Hi, welcome to this presentation from Java Innovations on the Vector API or SIMD programming for Java. My name is Paul Sandoz and I'm a member of the Java Platform group at Oracle, and it's my pleasure to introduce Sandhya, my co-speaker.
Hi, I'm Sandhya Viswanathan. I'm Principal Software Engineer at Intel.
Okay, great. So Oracle and Intel have been working on this API for quite a while. It's actually a fantastic collaboration, and I hope we'll continue to collaborate as we go forward. So what I'm going to talk about is a bit of goals and status of this API, get a sense of what it is, then introduce some terminology to help you understand a simple example I'm going to present and a little story. And then Sandhya is going to present some detailed examples they've done in Intel to show off this API and its performance. And then I'll give a little summary of where we are. Okay, so goals of this Vector API. So what is it? It's an advanced API for developing explicit data parallel algorithms. What you may have heard of in the past is something called single instruction multiple data, or SIMD model. It's designed to explicitly code SIMD style computations or data parallel computations. This is an API you might want to use when a runtime compiler in the Java platform, such as Hotspot, C2 compiler, or Graal compiler, cannot auto-vectorize or cannot infer from scalar code how to parallelize it in a data parallel way, or that the algorithms that it tries to apply, these parallelization algorithms, cannot be applied reliably. So the idea is you can write your algorithm explicitly and the compiler will do as it's told and optimize it. It's designed to leverage vector hardware instructions, and this is our source of data parallelism. So we leverage all these nice new instructions on the chip that are available to us. So in effect, the way you get your speed up or parallelism is that if you have one vector instruction, it can perform n operations in the same approximate CPU cycle as one operation. So you might be able to perform 8 add operations in the same time as one add operation, and that's where you get your speed up. It's designed to be cross-platform as well and support multiple CPU architectures. So in the spirit of Java, Java is designed to be cross-platform, and we try not to bias to one particular platform. So the design of the API is intended to support multiple CPU architectures that covers Intel, ARM, PowerPC, and potentially in the future RISC-V when that starts to become more established. But also it's intended to cover architectures within the same sort of broad CPU architecture. So we support Intel SSE, AVX, and AVX 512, and ARM is ARM Neon, and the up-and-coming SVE support as well. So we're broadly covering various different vector hardware architectures, and each have their own specific way of operating. And the API tries to hide out some of the implementation details of these. For example, on Intel, there is often a set of fixed hardware registers with fixed bit sizes of vector hardware registers. On ARM SVE, this is very different. You get one size, but the size is determined by the vendor. And RISC-V is even different from SVE. So it's very interesting, and it creates certain challenges for us to implement this API while providing the same Java API on top of all these implementations. So it's designed to be what I call a WYSIWYG API. And what you see is what you get API. Most of the operations or method calls you use on the Vector API have quite a clear mapping to a vector hardware instruction or a set of vector hardware instructions on supporting CPUs. And where you might want to use this, for example, you might want to write your own linear algebra library. You may want to do some image processing. You may want to do some character decoding. These are all use cases where data parallelism can be applied, and specifically SIMD style data parallelism can be applied. And our people are doing this today, and we want to enable that reliably in Java. We could also use this API within the Java platform itself. The Hotspot compiler, the C2 compiler, has a number of what we call intrinsics and stubs if you like, hard-coded subroutines that use vector hardware instructions. We have them for character decoding, string and array comparison, some cryptography, and so forth like this. Some of these could potentially be replaced by cross-platform Java code using the Vector API, thus reducing the maintenance. And we think we can pull these out of writing these in assembler or in C++ with assembler macros and pulling them out to Java code. And that will make our code base easier to maintain going forward. So status on the Vector API. The first release is going to be delivered as an incubating module in JDK 16. And you can enable it with a command line option. And the reason why it's an incubating module is this API is still experimental. We want to deliver it in the Java platform release, but we want to reserve the right to change the API based on feedback. We want to enable easy access for developers, but we also want to get feedback from developers. And this will allow us to sort of get a feedback loop. So the next incubating release we do will have improvements both to the implementation, but also enhancements to the implementation as well. And we're likely going to keep this experimental incubating loop around until we get new Java platform features that can improve the API, specifically with the features offered by Project Valhalla, which aims to offer value types and unify the type system between primitives and reference types. So it's work in progress. We're going to be working on a second round of incubation with enhancements to this API. We're going to be doing performance improvements with leveraging more vector hardware instructions, notably around improving the support for hardware masked instructions. It's both on Intel AVX 512 architectures and the ARM SVE architecture. So before I get into some examples, it's very useful to describe some of the terminology as a background. This is a bit sort of a chalk and talk side of the presentation, but I think if you understand what I'm talking about here, you'll have a good understanding of how the examples work. So a vector in the Vector API is represented by an instance of the class vector of the generic type E, and this corresponds to an element type. So a vector has an element type, and E is the box version of the vector's element type, so byte, short, int, long, and float. So int would be represented as E equals integer, because we can't represent generics with int yet. And there are specialized subtypes of vectors, such as int vector, which extends vector of integer. That's the way the public API is arranged. A vector has a shape, which we call a vector shape. And this is a size in bits. It could be 64 bits, all the way up to 512, or even max bits, which is determined by the runtime. So we can essentially, you can think of a vector as a bag of bits. For example, on the Intel CPUs, you can support 2 or more shapes at once at runtime, such as 128 bits or 512 bits, depending on the supporting architecture. ARM SVE supports just one shape, max, whose size is vendor specific and could range from 128 bits to 2048 bits, depending on what the vendor chooses when they're designing their ARM chip. And a vector has a species of vector species. So the species you can think of as a combination of the element type and the shape. And this represents the factory from which vector instances of a required element type and shape are created. So you can think of the vector species as the factory where you instantiate instances of vector, a combination of element type and shape. The preferred species for an element type is the species that has the most optimal shape for a given runtime. So given some CPU, its hardware says, well, I can support all these kinds of vectors of these shapes, but I prefer this one. And so the way we design portable algorithms implemented using the Vector API is we always use the preferred species. So we always get the most optimal shape and element for the element type we want for our platform. So we get the most optimal performance for our algorithms. And that's a crucial point. From this, we can write shape independent and optimize for runtimes that have different optimal shapes. So we could write our algorithm, it would optimize okay on Intel AVX 512, but it would also optimize okay on, say, an ARM SVE platform that has a different shape. And a vector has lane elements. And so the number of elements in a vector is the size in bits of your shape and the size in bits of your element type. So you can think of a vector as being a bag of bits, and you can slice it up into a bunch of lanes, and the number of lanes you have is dependent on the size of your element. So a vector whose shape is 256 bits, with an element type of long, holds 4 long elements and can perform 4 lane-wise operations at once, which means if we have this vector holding 4 longs, we could have another vector holding 4 longs and add them all together, and a resulting vector would contain 4 longs, each with the sum. And the way you might refer to this is long vector species underscore 256 in the API. As another example, a vector whose shape is 256 bits with an element type of byte, holds 32 byte elements and can perform 32 lane-wise operations at once, and you'd refer to that as the byte vector dot species underscore 256. So you sort of get the sense of what's going on here. So as an example, is just to visualize what's going on. A vector can be operated on. You can perform lane-wise additions. So the example I talked about before, you might have 4 long values packed into 2 vectors, and when you add them up, it adds them up in parallel. So A3 plus B3 equals C3 and so forth like that. You can also do, excuse me, cross-lane summation if you wanted to as well. So you can sum up all the lanes in the vector and get out a scalar value as well. There's just 2 examples in the vector API of what you can do. There are many, many more. And when Sandhya shows her examples, you'll see those crop up. Also, a vector can be operated on with a mask. So you can perform lane-wise addition with a mask. So not only do you operate on 2 vectors, you bring along a mask, which is effectively, you can think of it as an array of Boolean values corresponding to each lane in the vector. So here I have a mask of 1, 0, 1, 0, and where you have a 1, you perform the operation. When you have a 0, you take the value of the first operand, in this case, A2 and A0. I hope that's clear. So masks allow you to decide when to apply the operation and when not. They're also useful in this way if you're trying to model control flow in your data parallel algorithm. You'll often use a mask to decide when to choose and when not to choose based on an if and else branch to perform the operation. Okay, so here's the terminology. I won't go through all of this, what I've said, but it's useful summary slide in case you want to read through this later and remind yourself of what I just talked about. So on to the more interesting things, which is a little journey into data parallelism that is sort of I've been involved in for the last 6 years actually, which is array mismatch. So this is where I started off my journey into adding support for vectorization into the Java platform. So in Java 9, we added a method called array mismatch. This is a primitive to build on to implement methods array equals and array compare. So basically, given 2 arrays, you say at what index is there a mismatch between the elements? And we added 2 implementations of this: a Java implementation vectorizing using some misc unsafe and long values, and an intrinsic stub implementation contributed by Intel for the x86 platforms, and were contributed, I believe, by Red Hat for ARM. And these would use vector hardware instructions. So we wrote 1 implementation for x64 and 1 implementation for ARM. And then we can optimize this. So array mismatch would go through the intrinsic stub implementations on the right platforms. And then we can get superior performance for both mismatch, equals, and compare. But we can also implement this using Vector API with some degree of success. So here's the example of the scalar code of array mismatch. So for example, we're going to focus on mismatching of integer arrays, but this can apply to float, double, and so forth, all the primitive array types you're familiar with. So the array mismatch way it works is we take the minimum of the length of the 2 arrays that are input, A and B, and then we iterate through the indexes up to the minimum length. And we say, is the element in A and the element at B at I the same or not? If it's not the same, then we return the index of the mismatch. Otherwise, if it is the same up to the length, then we return the length, otherwise -1. If the two lengths are different, then we return the common length or the prefix. Otherwise, we say there's no mismatch and we return -1. That's it. So how can we vectorize this, or how can we turn this scalar code into a data parallel algorithm? So this is the way we implement it in the vector API. So first of all, we want to talk about our factory of how we instantiate vectors as our species. So we say, I want to use the preferred species associated with int vector. So that's our first line in the example code here. So we get a vector species of integer. And then we're going to use that in our the mismatch method to perform the mismatch implementation of the two arrays. So again, what we do is we take the minimum of the length of the two arrays, and then we have a different loop. Instead of looping over each element one by one, we want to loop over the number of lane elements that each vector holds. So instead, what we're going to do is loop over the bound of the length, species.loopBound length. This gives, because our array length might be longer than the multiple of the vector lane elements, we have to sort of chunk it down a little bit to go in steps of the lane elements. And then we increment by the species length. So we're going to get, if the number of lane elements was, say 8, we would go step 8 by 8 by 8 by 8 each time as we go through the loop. So we could do 8 calculations at once instead of 1 calculation at once. That's in effect what's happening here. So once we set up our loop and our bounds and our step, we then want to load a vector from array A and load a vector from array B at index I. So we use the int vector from array, we pass in the factory of so we tell it what the element type is and what the shape is from the species, and we get an int vector back for both A and B, VA and VB. And then we can operate on these vectors instead of operating on the scalars. So then we can do a compare, and we can say, is any lane element in A not equal to any lane element in B? And we can do this, say, 8 times instead of 1 at a time. So this is where we get our speed up. And then we can ask from the compare whether there is any elements that are not equal. And the way we do that is the compare returns a mask. And the mask says, will correspond to 1, saying the elements were equal, or 0, where the elements were not equal. And so we say, are any of the elements in the mask true? And if they are, we break out. And then we have to deal with the tail, since we're dealing with multiples, say 8 at the end. If the length was not an exact multiple of 8, we have to deal with the tail of our loop. So we just loop round, dealing with the tail here in the same way as the scalar code. Now there's a problem here that you may have recognized if we go back to this slide, is this is not optimal. So we're breaking out of our loop with any true. We're not actually identifying the index here when we break out. We're actually breaking out the loop and then redoing some work that we've done in the vector compare when we go to the scalar. Now this is not ideal, and we'll get to the reason why this is the case in the next slides. But before I wanted to do that, I wanted to show you the generated code that comes out of this loop. Now, if you remember that for loop with looping over the species length every time. Now, this is the generated code from Hotspot. Now, to get this code nicely fitting on the slide, I've switched off loop unrolling, just in case Hotspot decides to loop unroll, so I can put the hot loop of generated code here. And what we see is a this is why I talk about it being a WYSIWYG API. We can see an almost one-to-one correspondence with the vector operations in the API and the instructions that were produced by Hotspot. So we see the first 2 instructions correspond to the from array method on the int vector. Then the third instruction corresponds to a compare. Then we get a couple of instructions to deal with the mask, because we're reducing down values from the vector down into a single value to perform a test on. We can see the breakout, the loop. Also at the end, we can see the add of the species length, and we're adding 8 every time and going around the loop, checking the bound, and then going back and around the loop. So we're doing 8 at a time instead of 1 at a time here, and that's where we get our performance. Hopefully that's quite clear to you. it's not necessarily the case that all developers should have to resort to this analysis, but I'll get on to more in that in a later slide. Now, that is not the preferred code I would like to write for vector mismatch, and it reflects the current state of affairs in the vector API that we're working through and continually improving the implementation of the vector API to get optimal, but we're not done yet. It's a journey we've yet to complete. The ideal way I'd like to write this is to ask, is there a first true value that is mismatched? So I want to find the first true value in my mask that tells me the first index, which is not equal. And then I can return directly. All I need to do is then find the mismatched index and then add it to I and return it. I don't need to go round the loop in the scalar manner and find the index again, comparing values I've already compared against. Now, this does not work today because we have not optimized first true, but Sandhya assures me that we can do this. So the point here is the journey is ongoing. And as you're experimenting with the vector API, I highly recommend that you use a tool called the Java measurement harness to measure performance and look at the details like I showed you in the hot loop of the assembler to work out what's going in the interim of ensuring that we have all the vector API implementation optimal. Because at the moment it's not, you're going to run into sort of performance cliffs and you're going to wonder why it's not performing. And the best way to work out why is to measure. And measuring using JMH is excellent because you can use profiling, either perfasm on the Linux or dtraceasm on the Mac, and you can get Hotspot to spit out the hot loops of generated code and do that correspondence to the instructions and vector operations like I showed you. Often when the vector API is working well, there's a very easy what you see, what you get correspondence. When it's not working well, it goes all over the place and you'll quickly see that it's not performing very well. So the results here I showed you for the scalar mismatch, the vector mismatch, and the vector2 mismatch are measurements here, and you can see the difference. So I'm measuring throughput of each method. I'm measuring operations per millisecond, so larger is better. And so we see in my benchmark that the scalar mismatch is maybe 3x slower than the vector mismatch. But we see my version 2, my ideal preferred way to write vector mismatch, is actually slower than the scalar one. And that is because it's not leveraging hardware instructions, because the first, the method, what's it called again, first true, is not actually implemented yet. So what happens is, because it's not implemented as a vector hardware instruction, it has to emulate that instruction in Java code. And once it does that, it starts going very slow. And so when you're designing your algorithms and experimenting, you need to write benchmarks, and then you need to measure. And if you're unsure about what's going on, I highly recommend you contact the Panama Dev OpenJDK list with your example code and your benchmarks, and we can help work out what's going on and help decide what we need to fix and help prioritize. And that's often what people have done already, is they come to us with algorithms and we said, oh, this is not ready yet, or we've got a regression and so forth like this. It really, really helps us focus on what we should implement in the API. And also it helps focus on whether we have the API right as well. So I highly encourage you, when you're experimenting, to provide this feedback on the Panama Dev list to us, and it will help us a lot moving forward with the API. Okay, and with that, we're going to actually go into some more real-world examples. Sandhya is going to show some really interesting stuff and some, I think, some quite impressive performance results. So I'll hand it over to Sandhya.
As you mentioned, I'm going to show some more additional examples using different vector API features, and also show how to get the best performance from the underlying platform. Next slide. So as Paul mentioned, Intel has enhanced support for SIMD from 128-bit SSE to 256-bit AVX to 512-bit AVX 512. And correspondingly, the underlying 128-bit XMM registers have been extended to 256-bit YMM registers and 512-bit ZMM registers. The AVX ISA supports both 128-bit and 256-bit vector operations, and the AVX 512 ISA supports all three, the 128, 256, and 512-bit instructions. So it is possible for you to choose the best vector width possible for your algorithm with this flexibility. And also, as Paul showed, you could use the preferred species to get the largest vector width possible on the underlying platform. Next slide, please. So this is an example which is showing the dot product implementation in the scalar form. And what is dot product? It calculates the sum of the product of the corresponding elements of the two arrays. So here, left and right are the two arrays, and the corresponding elements are multiplied and then accumulated into the scalar sum, and the scalar sum is the dot product of this operation. Now, as you can see, this algorithm is highly data parallel and can be written using the vector API. So on the next slide, we show the one way to implement it using vector API. So this particular algorithm is implemented using the 256-bit float species. And as you can see, the core loop here operates on the vectors of size 256-bit, that is 8 floats at a time. So it multiplies the 8 floats, and then the accumulation is done here in the vector register sum. So within the loop, all the accumulation happens in the vector sum, and after the loop is complete, we reduce it to do the horizontal addition and reduce it to the scalar sum. So on the next slide, we show the generated code. As Paul showed before for the vector mismatch, here also you can see that the code generated by the C2JIT is very clean. You can see that there are 2 load instructions, vector load instructions, and 1 FMA per iteration of the loop. C2JIT has also unrolled this loop, and you can see going from one FMA to another FMA, there is a dependency on the accumulation vector. So as I showed you in the loop, there was one vector which was sum, in which within the loop we were doing the accumulation. So that sum is now in the YMM1 register. And there's a dependency from one FMA to another FMA on the YMM1. Now, FMA is a high latency instruction. So this code can be improved as we show on the next slide. So here, instead of using one accumulator, we are using 4 accumulators, which are independent accumulators. And after the loop is complete, and then these 4 accumulators are individually reduced to scalar, and the sum of those gives us the scalar dot product. The tail part after the loop could also have been written as sum1 dot add sum2 dot add sum3 and sum4, and then finally do the reduction. So on the next slide, we show the generated code for the hand unrolled code. So you can see now that the accumulation is happening in 4 different vector registers, which are independent: the YMM5, YMM2, YMM4, and YMM3. So here there's no dependency, and this code performs better. And on the next slide, we show the same code using the 512-bit vectors. And you can see here that instead of YMM used in the previous slide, and the C2JIT is using the CMM registers, which is a 512-bit register. So double the work is happening inside the loop iteration. So on the next slide, we show how the performance compares and how Vector API gives you significant benefit. You can see the scalar code. From the scalar code, the 256-bit vector code using one accumulator is about 7 to 8x better. And when we use multiple accumulator, we are about 14x. And going to 512-bit vector with multiple accumulator, we are about 21x the base scalar algorithm. So the next example that we show is a matrix multiplication example. This is building up on top of our learnings from the dot product. And here, again, you can see in the very core loop, multiple accumulators are used to perform the operation. And on the next slide, we show how Vector API helps to accelerate the performance of matrix multiplication up to more than 7x using 512-bit vector. So on the next slide, this particular slide is showing how to code the sepia filter using Vector API. Here, a couple of things that you can see the Vector API features that are used are the vector compare, which Paul also showed, and also the blend part of the API. So in this particular code, what is happening is that for each pixel, there are 3 colors, red, green, and blue. And the filter is basically applying, doing some arithmetic computation on each of the color. And after that, there is a saturation applied. And the saturation is performed using the compare and blend. So this is a highly data parallel operation, and that's why Vector API shows significant benefit. The other thing that you can see in this particular example is that we can pass a scalar argument to the vector algorithm. The API automatically broadcasts the scalar argument to vector and can perform the operation. So on the next slide, we show the generated code. And here, you can see all the red operations are for calculating the red pixel, and the blue for the blue pixel, and the green for the green pixel. If you see for each pixel, we are doing 3 multiplications, 2 additions, and then 1 compare and blend for saturation, and 1 store. So how does this code perform? So that we show in our demo on the next slide. And so here we are applying the sepia filter to all these images, both in the vector way and the scalar way. So the demo will show how the performance would be. So, so we'll start the demo now, and you will see that the second row is vector row, that the vector algorithm goes much faster than the scalar algorithm. And you can see that it is about 6 to 7x faster than scalar algorithm. So now we go to the next example, which is our Mandelbrot example. And here I'm showing the hottest part of the Mandelbrot. And this is a good example of how operations on mask are performed. So Paul showed in his example how masks can be used, but it is also possible to do operations on masks itself. For example, you can AND two masks, or you can OR two masks, and you can check any true or all true or first true, as Paul showed in his example. So the similar thing is used here also. So within this core loop, basically X and Y are vectors, and the first thing we do is to calculate the new X and Y, and then we calculate the square of those elements and then compare if it is less than the threshold. And then we generate the mask, and based on the mask, we decide whether further iterations are needed or not. On the next slide, we show the demo on a 256-bit platform, how the vector version goes faster than the scalar version. So we start the demo, and you can see that as the demo progresses, there's more and more computation needed, and the vector algorithm is faster than the scalar algorithm by up to 4 to 5x. Yeah, so so these are some of the examples to show you the benefit of writing code using a vector API. And I hand over to Paul to conclude.
Thanks, Sandhya. So what we saw there was a bunch of interesting examples. First was mismatch, which someday I will eventually get into the platform using the vector API. Maybe hopefully not in the next, hopefully not in 6 years, but sooner, when the vector API becomes stable and out of incubation. We saw some image processing examples, some, I guess you could associate with linear algebra examples, dot product, matrix multiply. The interesting thing about what Sandhya showed about the matrix multiply is although the vector API is platform independent, you can still leverage certain specifics of or be in sympathy with the hardware that you're operating on, so to remove certain aspects of latency. For example, I believe that applying the independent accumulators in that way will probably work on other platforms too. I'll have to verify that, but it's a great way of being in sympathy with the hardware if you're only prepared to run it on certain kinds of hardware. It's a great trick that you can leverage. And it's pretty impressive that Hotspot manages to sort of keep everything in the vector registers and not spill too much out on the stack. I believe we have some further work to investigate here to actually write some competitive matrix multiply kernels that you see in, say, Intel's MKL library or the Bliss Flame linear algebra libraries. I've been experimenting with kernels, and it's kind of possible to get close to what a handwritten kernel can do. Not quite. There's potentially some sort of tricks and tweaks we could do to get close to that, which is actually pretty impressive. So in summary, the vector API is designed to write data parallel programs, explicit data parallel programs using SIMD, and it is designed, as Sandhya has shown, to optimize on CPUs supporting vector hardware instructions. And I believe although the Hotspot C2 and Graal compilers can leverage some vector hardware instructions, this allows you to get access to pretty much every vector hardware instruction once we implement all of the operations, giving you much more a rich set of primitives to build up your algorithms. Very importantly, it's still work in progress, as I showed with the mismatch functionality. We need to expand our optimal support for operations and also expand it on the hardware. So our colleagues at ARM and other companies are working hard on ARM SV support, expanding it out there, and hopefully we'll get that into an incubating release soon. I would like to see integration with Panama's foreign memory API as well. So the examples we showed loaded and stored, loaded values from Java arrays and stored values back to Java arrays. But if you're working with off-heap memory, perhaps interacting natively, you want to load and store from native memory. And the way we do that today is through direct byte buffers in Java, but there's a better API coming, and it's already incubating in Java 16, that's Panama's foreign memory API, and we would like to leverage that instead of using byte buffers. So we'll see how we can enhance the API to load store to Panama's foreign memory API. Now, this API is likely to remain incubating for a while, and the reason is that we would like to leverage deliveries from Project Valhalla. Specifically around generic specialization. So when we talked about the terminology, we have vector of E, and E is the box version of the desired type we actually want to declare. We want to say vector of int. We don't want to say vector of integer. And when we say vector of int, perhaps there's methods only associated with ints and not associated with floats, for example. For example, the other way around, you may want to perform a Lanewise cosine on floats and doubles, but that does not make sense in ints. And so we think that Valhalla will enable us to better express the API we want to express for data parallel programming, but we're not there yet, so we're not comfortable with making it final until then. But in the interim, we'll deliver the incubating module in releases so developers can still use it, experiment with it, and provide feedback. And with that, I've finished. And okay, we have the safe harbor statements at the end, which you may or may not enjoy reading.